what a coincidence. I'm basically working on this in here right now, and sort of closing up QAOA with continuous quantum computing. And I came across in the past weeks, I sort of came across or interacted a bit with Jack Cerrone. I hope I'm pronouncing your name correctly. And I was like, I was taking a look at Jack's work, and I realized that he's got a blog, and there's actually a post about QAUA optimization with photonic quantum computing. So I thought, that sounds familiar. And I started taking a look at it, and actually, this is indeed, and it's July 2019, it's pretty fresh. So this is indeed sort of similar to what Mihao is trying to do with the Yellow Submarine project, but I guess I'm assuming it might be a bit different. I don't know. I didn't read this, right? But then, so you take a look at the disclaimer, and the first thing is like, so this is based on the math in this paper, and I open this paper, and who do I see there first? Guillaume Verdon. I hope I'm pronouncing your name correctly as well. Um, Basically, my favorite quantum influencer on Twitter, and I've been following these people anyway in Twitter, and it's like, interesting. That's from February 2019. It's also from this year. So cool. I thought I would just leave it at the Yellow Submarine. If this thing loads, my internet today connection is just a disaster. Um, yeah, but that might be something to take a look at as well. I definitely want to compare that because if I remember well, the version from Mihao and co is based on um, I think a quantum neural network architecture, and this might be something different. So it might be interesting to compare the results. And now I'm thinking, should I read the paper first? That looks super heavy. That looks indeed really heavy. Just I mean, it's fairly condensed. It's like 6 pages with references included, but and they take up like 2.5 pages. So, but that seems pretty dense. Maybe I'll just start from Jack's blog post. Try to reproduce his code as well. And then basically, oh come on, really? As this is not loading today, I'll just go through Jack's post. That's probably going to be the best thing. And there's even a circuit at the end. Okay, cool. Let's see. I mean, I don't know if it's gonna be based on the same problem. So it might be difficult to compare, but so here we're talking about the max cut problem. Let's see. Let's give it a try. Let me just the microphone. It's gonna just give me a second. I'll pause this thing for a second. Okay, so I'm not entirely sure whether the implementation algorithm is correct. Let's take a look at it. I basically wrote this paper and attempted to translate the math into an actual quantum circuit. Blah blah blah. Yeah, continuous variable optimization is an area of great interest, especially in quantum computation. The reason is, however, most of the implementations have been done as in discrete quantum computation. Correct. This is a good method for optimization. I can approximate the optimization of continuous functions to a certain extent, but in order to effectively, there's a typo here, I guess. In order to effectively optimize continuous functions and continuous variable optimization algorithm must be used. Yeah, okay, I get the statement. I mean, it might be. Yeah, let's go further. Not greater continuous pronunciation of Kwawa. I don't know if anyone pronounces this way, but that's what Wikipedia says, Kwawa. We can use photonic quantum computation algorithm. In this tutorial, we'll implement the algorithm using Strawberry Fields library. For photonic quantum computing, each optical mode in the simulation will correspond to one parameter, which is being optimized. For the purpose of our implementation, we're only optimizing one parameter, x. Therefore, we only need to use one mode. Okay. So this is not So this is not so far max cut. The purpose of this post is to act as a tutorial on implementing QAOA on the continuous variable QAOA algorithm outlined in the previously mentioned paper. For the purpose of this tutorial, I'm going to be implementing the algorithm for a basic function, which is a parabola that has been shifted by some factor, which we'll call a. So we wanna approximate that basically. Okay. To begin our algorithm, we have to initialize our mode, which represents the parameter we're optimizing. The guys who wrote the paper are very smart. They initialize the modes to a squeezed state, which will increase the variance of the x quadrature, the position, therefore having a greater likelihood of overlapping with our desired solution. Okay. I should clarify, to measure the resulting output of the algorithm, we perform a homodyne measurement of the mode. For this simulation, I decided, what was the homodyne? I think it was that you're either picking position and momentum or something like that. For my simulation, I decided to set the squeezing parameter of this state to -0.5, which squeezes the mode along its p quadrature and stretches it in the x quadrature. Coding zap histogram fields, we have this. Okay. But why does this? Ah, come on. I just can't understand how this cannot work. PDF. Oh, now it works. Cool. An x homodyne measurement. Now I get it. Okay, so you're basically saying that you're selecting the x. Okay, because here in the paper, basically, homodyne detection. And homodyne detection, photons are captured by a photodetector, which converts photons into electrons. This electric current is generally proportional to the number of photons, and wish to detect the quadrature or the Q mode under consideration. Exactly. So you're either doing an X or a P, I would say, homodyne detection. So you're picking what you want to measure. Okay. They initialize the modes to a squeezed state, which will increase the variance of the X quadrature. Because if we remember the squeezed gate, I think, so squeezed gate was doing shifting the uncertainty, right? So it's funny because the squeeze gate seems to me it works almost like a Hadamard, where you're exchanging certainty on one of the computational basis for uncertainty in the other, right? Just a wild thought. Squeezing reduces the uncertainty in either position or momentum while increasing the uncertainty in the conjugate variable. Exactly. I mean, it's kind of what you're doing with the Hadamard gate, right? At a really high intuition level, because you're going from your 0 or 1 in the z-axis to plus or minus. So you're getting full certainty on the plus minus computational basis, but you're then becoming completely uncertain on the other dimensions. It's sort of similar. Okay, so you initialize on a squeezed state, which will increase the variance of x. So what I'm assuming is, well, I can't paint in here. I don't know why. Oh, because I'm zoomed in. Interesting. Yeah, but then you guys can't read this easily. But I'm assuming that it's like, because I've seen some of this at the end, so I'm assuming that's, yeah, exactly. Oh, look at this. Oh, so I don't need to paint it. Okay, so that's the green is x and this is p. So you squeeze x. So you increase. Yeah. Exactly. Okay, so you're increasing the variance in there. The therefore having a greater likelihood of overlapping. I'll probably have to double check with the paper. Why is this minus 0.5? Or why did Jack choose minus 0.5, which squeezes the model along its p quadrature and stretches it in the x. Isn't the opposite what's happening? I mean, maybe I have the wrong understanding of squeezing and stretching, but it seems like the x is squeezed in here and p is stretched, unless you're thinking vertically and you're squeezing. No, you're stretching x and squeezing p. That would be an interesting thing to answer. Is it? Okay. Anyway, I'm still not sure where is this going, but so now we move into the bulk of the algorithm. In order to implement QAOA, we need to choose two Hamiltonians, a cost and a non-commuting mixer. This is in line with the mechanism of the originally proposed discrete variable quantum approximation optimization, blah blah blah, QAOA, as outlined in this paper. And these Hamiltonians are then applied repeatedly to the initial state, one after the other, for a fixed number of steps, which we call P. This means that we define our evolutionary evolution of the step of the program to be, however you got into that conclusion. See, that's an interesting, that's a more formal way of seeing this, because I've never really gone deep enough with QAOA either. I mean, I was like, at an intuitive level, what is it? What is it really doing, right? It's like, you've got the ansatz, right? And that's kind of, I assume, the cost Hamiltonian. And then the mixer. Now some things start to come, because if I start to make more sense, if I go to, because I recently published that, and then I think Jack answered as well here, and then in some of the comments below he actually does talk about the layer of our X rotations as the mixer as well. Okay. Which is basically what makes the all the so here's the quirk version. So this is basically what makes that would be the mixer thing, right? But my point here is, it makes no sense that this is at the beginning of the circuit. It should be at the end, because that's what makes the work that all your phase changing operations do here actually measurable, right? And so that would be so that would be kind of your the what Jack calls the cost, right? And that's kind of the mixer, this here. Yeah. But again, here in this example of the VQE tutorial from Circ, it's not clear why they've done it this way, because it doesn't seem to be correct. Then you apply that repeatedly. The reason for this is that general form of unit transformation. Okay. Since we know our Hamiltonians are Hermitian, we get valid unitaries to apply in our quantum circuit, where the total evolution of the wave function in the circuit is of this form. I'm still not really in shape with all that. It's probably simple math, but I don't feel like I'm in shape with this. We're often better our sets. Indexed by I of constant parameters that indicate the evolution of the system. They correspond to more concrete phenomena like the learning rate and gradient descent algorithm. But no, okay. Yeah, I mean, those are the parameters that you vary, right? In VQE, since the most Hamiltonian corresponds to a function that we're trying to optimize, since the cost Hamiltonian corresponds to a function that we're trying to optimize, we can write it in the form of a function we are attempting to optimize, but in terms of the x quadrature, as this is the parameter we are optimizing and measuring. This means we have this and our corresponding unitary being like that. Mhm. Notice how I eliminated the constant multiplier, as it just an as it's just an overall phase and has no effect on the state. Okay. Now let's consider the mixed Hamiltonian. We will use one of the examples provided in the paper, the number Hamiltonian. So where n is the number of modes in our circuit, and A transpose are the creation and annihilation operators. Since we're only working with one mode, we have what are creation and annihilation operators? Is that a thing? Is that a quantum computing thing, or mathematical operators that have widespread applications in quantum mechanics? Notably in the study of quantum harmonic oscillators. An annihilation operator usually denoted lowers the number of particles in a given state by 1. Okay, interesting. Learning a lot of good stuff in here. Okay, I'm really not getting any of these at the moment, aside from the first step. Let's see, let's just go ahead and then, let's go through all of it, and we're almost done. So, and then we'll probably redigest this. We've got to consider now how we will implement these unitaries in a quantum circuit. Well, this is actually simpler than it seems. We need to find optical quantum gates that correspond to 3 different unitaries. Well, luckily, these unitaries are of the same form as 3 common optical quantum gates: the quadratic phase gate, the momentum displacement gate, and the rotation gate, defined respectively as follows. Okay, so basically, so what's happened here? So, Mr. Jack, so it all comes down to this definition in here. This definition here, which comes from the paper. Or not? Does it come from the paper? The reason for this is that the general form of a unitary transformation is this. Okay, no, this, but where is it coming? Where is this coming from? Since we know our Hamiltonians are Hermitian, we get valid unitaries to apply in our quantum circuit. Because basically, so what Jack is doing is replacing the Hamiltonians, so mixer and cost function, here, right? In this case, this is the product, because it's just, you're applying it one after the other in the circuit. And then he goes ahead and says, okay, our mixer, I think there's a mistake in here. This should be H sub C, correct? Because that's the cos Hamiltonian, not the mixer Hamiltonian. Then he goes ahead and says, okay, our cost function is really exactly the function we're trying to optimize, right? So he's kind of doing it. So instead of thinking, because I usually come from another angle, right? But this makes, from a mathematical perspective, total sense, where you're basically saying, okay, what do I want to optimize? So first you express what you want to optimize, and then you're going to try to find a set of gates that approximates that, or that allows you to do that. And I think that's basically what Jack is doing here. So this is the function that he just expands on this, and it's always as a function of one of the quadratures. I wonder why you I wonder whether the choice of x is just an arbitrary choice, or you could just choose the momentum quadrature as well. Um, anyway, then he just goes ahead and replaces that here based on this formula. Then as the mixer, he just picks the number Hamiltonian. That's something that comes from the paper, and I'll probably have to um, read that to understand why. But this I'm not familiar with this and with the annihilation and creation operators. But then he goes ahead and does the same, right? So, mm, and so basically now he says, so when it comes to constructing the circuit, we have to consider how we will implement these unitaries in a quantum circuit. And then he says, well, you've got those gates which basically um, have a similar form. Doing some simple algebra and setting, whoa, okay, y, h equals to h. I mean, that's not, what's that? I don't know what's that. But basically, he goes ahead and says that's what. So with these, if setting the variables like that, and using them here, you basically get those expressions. So we can implement the strawberry fields code. We can then implement this in strawberry fields code, building off the code for our initial state. For this implementation, we'll make a function that we can repeatedly call based on the value of p. Run circuit. So that's the initial state squeezed, and then basically he applies the sequence of beta parameter of a parameter, beta parameter, parabolic minimum. I guess those are these betas and alphas. Where alpha parameter, beta parameter are sets of parameters and is our value of a. Oh yeah, okay, cool. After these, all that is left to do is measure our mode with an x homodyne measurement. I guess if you would choose the p quadrature, you would do a p homodyne measurement. Now, in order to find optimal values for our sets of parameters alpha and beta, we have taken a fairly simple approach and simply sample from a predefined list of constant values for a fixed number of iterations. So it's basically the same what the VQE tutorial from Cirque is doing, right? Read the docs. Because, I mean, here you could use any fancy technique like from gradient descent or any fancy optimization technique that would allow you to vary those parameters. But basically what they do in here is just looks like it's been updated. Oh, growth, that's not what I want. I want circ. Here it's basically the same they do here. They use this, how's it called, the lean space, all these things here, find the minimum. So they just do the run sweep. So they just do like a basic, let's run through different possible configurations of values. And I'm assuming that's exactly what Jack is doing in here. After the opponent chooses the parameters randomly, it runs the program a fixed number of times, taking an average of these trials and calculating the loss of the obtained value. If the loss is less than the value of the number is updated along with the variable, so we're trying to optimize. When this part of the program completes, the optimal alpha and beta sets are taken and repeatedly run, and an average is taken to make sure that the chosen alpha and beta yield a probability distribution that is close to the expected optimized value of our function. here's the complete code for my simulation, including the method that I used to find optimal values. Okay, so that's complete code, which in the next video I'll try to probably run. Yeah, I'm gonna try to run that in the next video, and then here you've got the first step. So you've got like a squeeze after the squeeze gate. Second step, third step. As can be seen, after 3 steps, the peak of the x quadrature is located around 1, which is the expected optimal value for our function. Keep in mind that the algorithm does not work a lot of the times, as not all values of unfair actually lead to circuits that correctly find the optimal value. These values have to be chosen based on the context of the problem being solved. Okay, thank you. It's interesting. It's a bit of a, it's quite a different approach than I think what Mihao is doing, because they use a like a CVQC, like a continuous variable quantum computer. I can't with those long names. Like a continuous quantum computing neural network, I think. Whereas here's pure QAOA, I would say. And basically what it all comes down to is how can you build a circuit so there are 2 things in here. So one is, how do you come up with your, I mean, I don't know if you can call it ansatz or not, right? But this is basically that portion of the circuit. That portion of the circuit. And this is what Jack is working here out with, taking those gates and then saying, look, that's, you know, that's what we need is we need these, and then we need the mixer, right? So basically you need to apply like this, and these sort of consecutively, and so he translates that into a circuit by basically taking those existing gates. But intuitively that's just, there's no, I can't really extract an intuition out of this right now. Those are, well, what are those gates? Those gates are the phase gate, the momentum displacement gate, and the rotation gate. But that doesn't really, because that's really, you know, I'd like to get sort of a feeling at the intuition level of why this kind of makes sense. Because mathematically, as Jack says, you just, you know, just go through the equations and then basically figure out what's the best choice. But that doesn't feel, it's not something, it's not, I don't know, that doesn't feel like, it doesn't tune with me. I'm just maybe a bit too romantic with that, I would say. And this is still also what intrigues me a bit. So why does Jack pick H2 H? I don't know what this H is. Is this like a whatever constant in physics? Yeah. Good. But there's a lot of those bits and pieces here that are clearer now than, you know, a couple months ago when I really first time started reading about continuous variable quantum computing. Cool. So I'll try to run this. I'll try to run the code as well. I'll try to kind of read through that maybe again. Read the paper from Guillaume, which is this one. But that, man, I'm scared of that. That looks dense like hell. Interesting. That looks really dense. I admire that, man. I mean, really doing this type of work. This is just. This difficult. Yeah, and then I'll go ahead and then let me save the paper already. I think it was the reference. Where are the references? Hope you're not getting dizzy with my scrolling. I think it was the reference 12 or reference 11. No, yeah, CVQ, so continuous variable quantum neural networks. I need to save that. And because that's basically the one that's used for the architecture for Mihao's project. Cool, perfect. Whatever, that's not working. Anyway.